Hi Adira, I want to say a couple things about number 6 and number 2. So let's start with number 2. So here's the question, you've probably read it before. It says, let S be the solid obtained by rotating the region around the y-axis. And here's the region. And so let's just talk about part A first. It says, explain why it's awkward to use slicing to find the volume V of S. So I'm going to try to draw a picture of what this three-dimensional object is going to look like after you rotate it around the y-axis. It's going to look kind of like a red blood cell with a little central depression. Sounds like a good name for an alt country song, Central Depression. So it goes kind of like this, right? Um, so I'm sure my drawing is not great, but this is kind of what it's going to look like in 3 dimensions. And it's also a little bit disgusting, like somebody stomped on an eyeball or something. But so what is it going to look like when we cut it various ways? So we're trying to explain why the simplest thing in our toolbox would just be to use the area of a slice function, right? To use the area of a slice function and then just sum up all the slices and that gives you the volume. So that's pretty easy. And we're trying to argue why that doesn't work here. So there are basically two ways that you could slice this thing. So suppose you slice it, I mean, you could slice it diagonally, but that blows my mind. So let's say we're either going to slice it diagonally or diagonally. We're either going to slice it vertically or we're going to slice it horizontally. So suppose we slice it vertically. And so consider what these vertical slices are going to look like. You have to kind of imagine the same thing going on over here. So what is this going to look like if we pull it out? It's going to have kind of an odd shape. It's going to have a flat bottom, and then it'll kind of go like this, right? There's going to be a little valley here for the central depression. So the point here, these cuts are going to depend on this x. So if you're going to use the area of a slice approach, then you need to be able to express the area of this valley thing just as a function of x. And the problem is that that's hard because it's not just like a circle or something that just depends on the radius. This seems to be kind of a more complicated shape, and I'm not really sure how to write down a formula that describes the area in terms of x. So that's the basic reason you can't cut it vertically. So why can't you cut it horizontally? So let me hit Control Z 1,000 times. And let's consider what would happen if you cut it like this. Oh, shoot. Like this. Okay, so if we cut it like this, you have to imagine that it's gonna, what would it do? That would like cut off kind of a little ring around it, right? That's what this cut would do in 3 dimensions. So we take the lid off this thing and we look at it from above, and so there is one good thing that happens, which is that this makes a washer shape. Okay. All right, so washers are simple. Washers, the area of a washer can be described in just two numbers, the inner radius and the outer radius, so that gives you some hope. The problem, though, is that the inner radius of the washer, for instance, is going to be like this length. Okay, and what is this? This is basically x as a function of this y value. Okay, so if you have to know this because you have to know the inner radius here. And how are you going to find it? To get it, you have to solve this equation for x. But the problem is that this is a cubic polynomial. This is degree 3. So solving for x is going to be a real nightmare. So it's real hard. Um, and so that's why you can't do that. Okay, and that completely answers the question with these assumptions. You know that you can only cut it vertically or horizontally. So that takes care of part A. And part B says sketch typical approximating shell, blah 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 blah. So let's try to do all that. Okay. So let me make some space. All right. So we're going to use cylindrical shells, and so what does that mean? We're going to make imagine a little thin bit of this thing here, which I'm going to pretend like is totally flat here on top. And it's going to spin around, and that's going to give me one shell of this shape. So this is going to end up being really terrible because of my palsied handwriting. But we're taking a little thin shell, you know, in here. So what we're going to do is we're going to figure out the volume of that thing, and then we're going to add all those up using an integral. Okay. So the way this is going to work is that the width of the thing is going to be delta x, and you can see that the height of the thing is going to be just a function, right? So this is f of x. It always works like this for cylindrical shells. And then when you spin it around, you're basically going to get a circle that has what? That has x as its radius. And so, you know, the circumference that it makes is just the same as the circumference of a circle with radius x. And so the circumference of the shell is going to be equal to 2 pi x. That's just the formula for the circumference. Okay. And to get the volume of the shell, you just multiply all these things together. So the volume of this shell is going to be 2 pi x, f of x, delta x, and then you just sum all these up to get the true volume of the shape. So 2 pi x, f of x, and dx. And right, so now instead of writing f of x, you have to copy in what this function actually is. So you do have to do a little bit of an integral. You have to do the antiderivative of a fourth degree polynomial with some constant junk. But it's not that hard. And so that gives you the answer to, right, so we just did all these things. So now we're done with 2, okay? And let's go on, maybe I should stop this and do the other problem in a separate video. Hold on.